Magnets, they seem simple, holding notes on your fridge, guiding your compass, powering motors. But beneath the surface lies a world of quantum behavior and invisible forces that scientists are still trying to fully understand. Now, in a stunning twist, physicists have uncovered a completely new form of magnetism, one that breaks the traditional rules of magnetic behavior. And if this discovery can be harnessed, it might change the future of technology forever. Welcome to Deep Space Unknown, where we explore the strange, the mysterious, and the universe's hidden science. Subscribe and join us as we dive into the unknown. What is magnetism? Basics. To understand this new form of magnetism, let's first take a quick journey into the magnetic world we already know. Magnetism comes from the behavior of electrons, tiny particles that spin and create tiny magnetic fields. When lots of these spins align, we get a magnetic material. The two most well-known forms of magnetism are ferromagnetism, like iron or a regular fridge magnet. In ferromagnets, the electron spins all point in the same direction, reinforcing each other to create a strong magnetic field. Antiferromagnetism, a more subtle type. Here, the spins line up in opposite directions. One spin points up, the next points down. As a result, the magnetic effects cancel each other out. There's no overall magnetic field, but the material still has hidden magnetic order. For decades, physicists thought these two types covered most magnetic behavior, but nature had a surprise waiting. Altermagnetism, a new kind of magnetism. In 2019, theoretical physicists predicted something strange, a possible new magnetic phase they called altermagnetism. It wasn't ferromagnetic, it wasn't antiferromagnetic, it was something in between. Fast forward to 2024, and experimental proof finally arrived. Using cutting-edge X-ray techniques at the Swiss light source, researchers observed altermagnetism in a compound called manganese telluride, a material previously thought to be a regular antiferromagnet. How altermagnetism works. So what makes altermagnetism so unique? Imagine a pattern where electron spins still alternate like in antiferromagnets, up, down, up, down. But now their quantum energy levels also alternate in a special way between spin-up and spin-down bands. This creates a totally new kind of spin behavior, one that doesn't generate a net magnetic field, but still has a complex directional spin structure. Altermagnets behave as if they're hiding their magnetism in plain sight, undetectable to ordinary tools, yet incredibly ordered on a quantum level. Why it matters. Spintronics and future tech. Now here's where things get exciting. This discovery isn't just academic. Altermagnetism could revolutionize spintronics, a next-generation technology that uses the spin of electrons to store and process information. Today's electronics rely on electron charge, but spintronics taps into the magnetic spin, offering faster speeds, lower power use, and greater data density. Unlike traditional magnets, altermagnets don't produce messy, stray fields. That means we could build tighter, more stable circuits with less interference. Think of ultra-fast memory chips, data centers that run cooler, or quantum computing components that need stable, exotic magnetic states. Altermagnetism opens the door to all of this. Real-world applications of altermagnetism. So what could this mean for everyday life? In the near future, we could see hard drives that store data using quantum spin, lasting longer and using less energy. Mobile phones and laptops could run cooler, faster, and more securely. Even medical imaging could benefit, with magnetic resonance systems becoming more compact and accurate thanks to zero-stray field technology. Engineers are already dreaming up spintronic processors that blend memory and logic together, making devices smarter and faster at the same time. Another twist, P-wave magnetism at MIT. But altermagnetism wasn't the only surprise in 2024. Physicists at MIT announced another strange new magnetic state, something called P-wave magnetism, discovered in a two-dimensional material called nickel iodide. In this state, electron spins form a spiral or wave-like pattern, a kind of magnetic dance. Even more incredible, these spins can be switched using tiny electric fields. This could lead to ultra-low power memory devices, sensors, and new ways of building quantum technologies. The discovery of both altermagnetism and P-wave magnetism in such a short time hints at a new age of magnetic science, one where we're just starting to crack open the surface. Expert reactions and scientific buzz. The scientific community is buzzing. physicists across the globe are calling altermagnetism one of the most important magnetic discoveries in recent decades. One researcher at CERN described it as unlocking a hidden symmetry in nature we never thought existed. Journals like Nature Physics and Physical Review Letters have begun fast-tracking research into similar materials, hoping to find new altermagnets or expand the theory behind them. This kind of rapid attention usually means one thing: something revolutionary is coming. Challenges ahead. Of course, we're still in the early stages. Right now, these magnetic phases can only be observed at extremely low temperatures, close to absolute zero. That's not practical for your smartphone. Not yet. But researchers are now hunting for materials that can show these properties at room temperature. If they succeed, we may see a whole new generation of magnetic technology emerge within a decade. Strange magnetism beyond Earth. Let's take this to space. Could altermagnetism, or even P-wave magnetism, naturally exist in the universe? Inside the dense cores of neutron stars, where magnetic fields are billions of times stronger than Earth's, it's possible that these exotic spin patterns exist without human intervention. Or deep within the crusts of frozen exoplanets, where temperatures are naturally close to absolute zero, altermagnetism could already be shaping planetary magnetism in ways we haven't imagined. Studying these quantum effects on Earth might help us understand the powerful magnetic anomalies seen across space, from pulsars to magnetars and beyond. From your fridge magnets to the strange spin dances of electrons, magnetism remains one of the most fascinating and still mysterious forces in the universe. With the discovery of altermagnetism and P-wave magnetism, physics is entering a bold new era. And we'll be here to break it all down for you. If you enjoyed this deep dive into the unseen world of quantum magnetism, give us a like, subscribe, and ring the bell so you never miss an episode of Deep Space Unknown. Thanks for watching, and as always, keep exploring the unknown.